Hi everyone. I hope you are having a great time at the gala event. I'm glad to have you all join me in the session where I discuss about how to build scalable machine learning systems. I am Vidhi Chugh, founder of All About Scale. Let's get started. So before I delve deeper into the technical details of scale, let's first discuss why am I talking about scale today. You may think it because I'm bullish about scale, well, which is partially true. Still, it's largely because I have experience building scalable machine learning systems while working in mini startup environments of Fortune 500 companies. So, the mini startup culture within those enterprises who are on a journey to digital transformation, it does sound like being at the right place at the right time, isn't it? But it's way more challenging than how cool it sounds. There are a lot of lessons learned during that journey, which is precisely what I've condensed and I'm going to share with you all today. So now that you know, I'm not one of those writers who talk about 80% of the POCs don't make it to production, these type of articles written in top publications, but rather I'm someone who's seen the good, bad, and ugly side of how to take the models to deployment. I advocate designing frameworks and guidelines, which means that I have an eye for identifying common patterns, something that I've learned on the job while being a data scientist. It's natural to us. So I've identified there are some common threads that connect all these organizations and the corresponding solutions. Something that I call as what works when, WWW. It involves the breadth of system design choices and the trade-offs that we take while building scalable systems more efficiently. So let's get started. To start with, let me just ask you one question. What comes first to your mind when you think of scale? Scale rings generally bells in terms of infrastructure, data, growth, users, and number of other words that are listed on the slide. These have come across in my discussion with a lot of industry practitioners. So we'll take them one by one. Let's start with data. So the rapid rate of digitalization in the recent years has led to an exponential increase in data generation, which is what we call as big data that highlights the scale at which data is made available these days. And next one is infrastructure, computing power, which is what has happened because of latest technological advancements. The computing power, it has become accessible than it was ever before. But there is still one thing that sums up all aspects of scale very well and it's written on this slide, which is growth. Growth could be in terms of data, system requirements, number of users who are going to visit your web page, or the application, or their expectation from the application, that the kind of workload you need to support. So now that we've touched upon the users aspect of scale, let me share an interesting story with you. Story is how we understand most of the concepts, and we remember them after my session is done, maybe. So it brings forth what can go wrong if you cannot foresee user growth. So we've talked about users in the previous slide. Back in 2004, thousands of passengers were left stranded during the Christmas season. You must be thinking why. It's because an airline was using 10-year-old crew scheduling system which crashed. And it happened because the system could not support more than 32,000 schedule changes in a month. This shows how anticipating the impact on the resources that are needed to support, or the workload that is to support the workload corresponding to the unexpected demand change, or the surge in demand. This is a very, very difficult problem to solve. It's very challenging. Now, fast forward to recent times when ChatGPT was launched and it received whooping 1 million user visit within a matter of 5 days. So if I just share this information with you, it might not sound crazy. You would be thinking, why am I talking about it, right? So let me give you some historical data points that prove the worth of it. Something like Netflix, if you can see on the right side, it took 3.5 years for Netflix back then in 1999 to achieve this kind of scale. In recent years, Instagram and Spotify, they've been able to achieve this in a matter of few months, but ChatGPT raised it up within a few days of its launch. You must be wondering the reason behind this exceedingly or supremely fast speed or the feed that they were able to achieve. It's because we live in a digital world where the launch of ChatGPT enabled the world to use it at a wider scale, and that too very efficiently. They were able to make use of it at their workplace, where they're able to bring more efficiencies, and everybody wanted to make use of it. But OpenAI, did they anticipate this coming? Did they know that it's going to hit that kind of scale, or so it will draw attention from the world at this scale? Or maybe not, because their system got throttled after a point. So that's where I like the pace at which they not just brought the scale, but also showed to the world one thing that I like about business and the word that runs the business, basically, that timely materialization of skill can result in monetization. And that's what they did. That's the route they took. So now they were aware that there is a market demand, and they launched the ChatGPT enterprise version, asking people to pay for a premium for such advanced service. So the $1 million question that arises from the anecdotes that I shared on the last slide is, how do we know that it's time for scale? And the answer is, well, we don't know. And maybe no one knows. We all start with informed guesses and then continue to make some system design choices that help us in keeping the system afloat or scaling the system or managing those increased workload. Now that I've mentioned the word workload, it's important for me to tie it back to the definition of scale. That it's not just about handling the increasing workload without thinking that I might not need to add some additional resources. But our goal is to be prepared to manage the increasing workload with a cost-effective strategy so that we can leverage the resources that extend the system's capacity. There's a difference in these two definitions. And they're very well mentioned in a document that I was reading from CMU, which was dated back in 2006, I guess. So it's very important to highlight that this system monitoring, this is an ongoing exercise which requires varied system design choices, which requires multiple trade-offs throughout. All right. So the visual that you see on the screen, it shows the increasing demand on the x-axis and the corresponding response metric of the system on the y-axis. The longer it takes a system to respond, the more time it takes, for example, to load a website. This is kind of a risk. It's equivalent to a risk that the user might drop off, right? So I'm coming from the world of risk management, so I know that the commonly used terms that we all must have heard of at some point in time is categorizing risk as low, medium, and high risk, which is what I've labeled here as safe, alert, and throttled. And I've given them those colors that show the intent of what they mean. So as we can see, how the system is about to reach the alert zone when the first surge in demand happens. That's when maybe an engineer comes into the picture, brings in some additional resources, maybe adds some extra memory, and then brings it back to the safe zone, which is acceptable zone for us. Similarly, the next time when that breach happens, more resources are required to pull it back until you see the third time. That's when the system reaches the high risk zone. It breaches that maybe alert zone and it becomes throttled. That's precisely the state we don't want. We want to avoid that. So how do we do that? For us, to make sure that that doesn't happen, we need to be prepared. Our goal is to be prepared. And how do we do that? The monitoring process. It requires us to continuously monitor. Like I mentioned previously, this is ongoing process, but it must be automated and it shouldn't come as an afterthought. So that's why precisely the POCs fail as well. That, well, everything is done, the value proposition has been calculated, and we know that the experiment proves there is a value in it, and it's time for us to scale, or it's time for us to take it to production. That's when the issues related to scale, integration, technology, tech stack, having that ML in that as one small component in that entire engineering pipeline, that's when those intricacies come up. And that's what I want, that it should be a very well forethought process. And for example, when a lot of people, they do such exercises of how do we reduce the time and space complexity if we give you this dummy toy problem, right? So you are aware of more efficient data structures or maybe algorithms, but they're able to help you manage that computational efficiencies up to a scale. It does bring that. But after you have exhausted these options, there's a point after which you'll exhaust that. And but what would you think after that point? That is this the be all of it? But we need to look beyond. So now the system must be designed to scale, even if the number of users who are visiting your web page or using your application, even in the black swan event case, the system should be able to support that. And for that, you need to obviously seamlessly add resources to ensure that there is no downtime for the user. Now, with the introduction of cloud technologies, this headache is kind of taken care of, which is related to infrastructure. But the number of system design choices or the trade-offs that we need, they don't end there. Like, you really need to keep making use of different components of the system that is picked for varying scales. It could be your data processing pipeline tools like Airflow, or Python API tools like Flask or Fast API. The choice should always depend on the functionality. Now that we've written efficient code base, which is supported by the best choice of infrastructure and all those modules, right? You must be thinking there's still one question that remains unanswered, and that's something I really want to emphasize while we are on this slide. That we are living in the world of machine learning, advanced algorithms, cutting edge, sophisticated the algorithms, right? Having discussed all of these as problems, does it strike to you that there is one still core issue that would we really react to the situation? It's more like having a reactive approach, that when things will break, there would be an engineer who would do the kind of last minute changes, firefighting situation, and bring the system back into the state it should be in. Certainly not. This is not the way we should approach, right? Certainly not now that we have enough compute and the data that we are saving to learn from the historical incidents about when the system is approaching that state where the additional resources need to be pulled in. So there's a predictive scaling approach. What it does is it lets you focus the demand for the infrastructure so that you can dynamically scale it up before the surge event. Now, I know what question you might be having is that this is probabilistic, right? Because by the very nature of machine learning algorithms, there is a certain accuracy level at which these phenomena work, right? Now, this approach still has two benefits. Let me share how. One is that you can maintain a high level of service throughput. And the second one is that you only pay for the increase in load at the time when it is required. So it's still a good bet. It gives you that lens through which you can analyze or maybe foresee what's coming and then adjust the resource need. Something that I mentioned, that anticipating it is a difficult problem, right? So you are able to calibrate it and then still have a very healthy system state. Okay. So we understand, so it's time we understand the characteristics of a scalable system. I'll quickly do that in these 4 pointers. And let me bring them up. So your system must be able to handle the varying load, which must be clear by now, given that I've talked about 2 definitions of scale previously. And it should support big data processing, efficient computing. All these 3 are part of it. And I discussed them very fast. The reason for that is there is a very important point on the slide which I want to highlight, that swift response. This is crucial for specifically machine learning systems. And the reason is that most of the machine learning predictions or the output or the response coming from ML application, they are very time sensitive. They're very short lived. There is a reason that those predictions are coming. For example, let's consider a trader who needs a response from a stock prediction model. And they need that information to execute on a particular trade. And I'm not in that profession, but I know that they need that input or the signal, as we call it, from those models, which is needed at that very moment, right at that moment, maybe within a fraction of a second. That information is needed to take that call of whether I should go ahead with that trade or not, right? So the swift response is one of the key characteristics of a scalable system. Okay, so you must be thinking that my teams are doing a great job building systems that can scale. But Vidhi somewhere mentioned earlier in her slide, right, that it shouldn't be a afterthought. So what are those indicators, some early indicators that tell me that I would soon hit the problem of scale? Scale is going to be a problem for me soon. Or is there a way for me to have that leading indicators right before it happens? Or it could totally happen that maybe your team is already going through it. So you can hear it in those conversations when your team is struggling, waiting for long hours for model training to complete. And I've seen it firsthand. I was working on large language models. And I know you must be thinking, Vidhi, these are pre-trained, which they are. But let me tell you that even one epoch of fine-tuning these large models, it took many, many hours. So what I did as a makeshift arrangement, and the workaround is that, I used to begin the model training process on Fridays, and used to think that first thing in the morning, Monday morning, I'll go and check whether I'll check the results of those experiments and see whether they qualify, what should be my next course of action. And I know that this is not sustainable, but and more so because the data scientist time is not supposed to be spent waiting for the model training to complete, because they use this information to understand which experiment is promising, and can I make use of it, should I double down on this further, and accordingly decide the next course of action, because ML projects are very iterative by nature. Which takes me to my next point, that if your team is going through such issues, they will soon come to you asking for bigger and better machines. And the premise of that is, like I mentioned before, machine learning experiments are iterative. You need to really conduct a lot of experiments, that too at scale, to decide the right model, right algorithm, right parameters. Now, this gives a good segue to understand the cloud economics part of it, which kind of ties it back to strategy. So I'm an AI strategist as well. So while you're designing an AI strategy, you must be having reasons about why we started this project. There must have been some good business value proposition. It could be about, this initiative is going to help me make better business decisions, help me understand historically how the businesses was run, what worked for us, what did not, what should be avoided, or maybe it simply opens new revenue streams for me in the business, or it brings more operational efficiencies through automation, or maybe scope of error reduces, right? So in essence, the return on investment of any initiative that we take, it must have been accounted for somewhere right at the beginning of it, at the strategy level, when we were comparing multiple initiatives to pick, like which one should be picked, right? Now, the ROI in itself is not a complete metric. One must consider the net ROI, something that is not very frequently used as a term. And this is because of the same reason that I discussed, the cost that we spend on facilitating the cloud resources, or those powerful machines that are enabled with GPUs and TPUs accelerators, the cost associated with them is very expensive. They are very costly. And they eventually impact your bottom line, which is, you can compare the net value that's generated out of the project is kind of taking a hit, because there's a lot of cost factor that goes into helping the teams have those bigger, better machines on which they can run those experiments at scale. Now, the last point on the slide is, another common issue that we've seen is, while you're training a model, the developers frequently encounter such error, which is memory insufficient, something of that line, which stops the training process, hinting that it's time for increasing the memory allocation as well. Okay. So we understand the problems by now, and it's time to know some of the design choices that can be made at the right time that can help us address those, or because we've identified the risk, so we can't just sit with it. It's time for us to think of measures, how we can mitigate them, how we can timely address them. So the very first is, I hate to say this, but we all are living in the world of abundance. In terms of data, it means that we have access to more data. Like I mentioned, that the rate of data generation has exponentially increased since the rapid digitalization over the past few years, which forces us in a way to think that the more data we have, the better it is. And maybe it's not just about data also. It's, people also think about, hey, the range of advanced state-of-the-art algorithms that everyone wants to leverage to solve the greatest of their business problems. But what we also need to understand that key to successful or machine learning projects is generally not going after the next big thing. I know that this is a difficult statement to make, but what it requires is instead to work on the foundations, which is one thing that's maybe a new term, but not many people still follow it, which is becoming a data centric scientist. What it means is we all are data scientists. What does it mean to become a data centric scientist, right? Because I'll tell you the difference. Because it's easy to let the data pipe in through many of the algorithms and to understand which one is the best performing one, and you start focusing on that coding, building the pipeline, and bringing everything together. But if you focus on high signal rich data, which accurately represents the process or the phenomena that you're trying to model, this is very crucial for the success of your model. So not all business problems, they require bigger algorithms. There are still a majority of challenges in the business that can be solved with relatively easier to manage algorithms. Okay, so while this discussion on design choices, how to build scalable system, this is a big literature on its own. And the key problem with this is that till now, there is no go-to rule book or something where you can just read and say that, okay, this is set in stone, I can do that. And, maybe this is taken care of. Instead, this is largely the institutional knowledge coming from folks who have experience, first-hand experience of managing those systems at scale. You really need to be in those firefighting situations many a times, see those nuances to understand what works when WWW that I mentioned at the beginning of my talk, right? That's what precisely I've done. I've tried bringing that institutional knowledge to all of you in a short span of this discussion, but definitely there is more to it. It requires building a lens of making those right system design choices throughout the machine learning project lifecycle. This is not just done once, I've added resources, system will look after on its own. It doesn't happen. I mentioned that it's more like monitoring it, and obviously you can't make a person just sit and monitor it. So we've talked about the automation aspect of it as well. So by any means, this is not a trivial problem to solve. So if you are interested in learning more about how you can prepare yourself, then it's time for you to scale. You can feel free to reach out to me via LinkedIn. Vidhi Chugh is still not a very common name. So, or you can maybe scan this QR code in the meanwhile to visit the webpage, to visit my website, to join the waitlist for my upcoming course on foundations of building scalable machine learning systems. That's where you'll get to know more about how to make those trade-offs, starting from identifying the problem statement to how to take an idea to production. So you can go and refer the course. It's listed there. It's going to be out soon. Okay. So with this, my session has ended, but I'd be happy to answer any questions if you have.